So anyway, here, so the sensitivity is a little bit worse by a factor 4 or 5, right? But it also takes much longer, something like 30 years or so to achieve this precision, right? And then there is also click, right? But of course, nobody is telling you that, you don't want to change a little bit the time, the running time, right? So things will scale with statistics. So you could draw yourself the same kind of diagrams, to reach a given precision in the X coupling, how long it will take, right? So you start with this baseline point, but, maybe you don't care about reaching per mil. You are fine only with 5 per mil. And then in that case, it will take a little bit more than 1 year. And then you can compare again, how long it will take for ILC or for click to actually reach the same precision at FCC, right? And then you see that it will take basically 50 years, right? So this is a comparison which is important, because you want to compare the various projects for a given physics output, right? For the given number of Higgs boson that is produced, or for the given precision that you can achieve in the measurement of the couplings, right? And of course, the more time it takes, the more power you need actually to use, the more electricity you need to use, right? So this plot is very similar to this one, except that in the y-axis, you don't report the time it takes, but the electrical consumptions, right? And here again, you see that basically FCC is really the clear winner, right? So it could be that indeed the power, so this means that the amount of electricity, instantaneously is lower at a linear collider because, you don't have radiation synchrotron. Nonetheless, if you convolute by the number by the amount of time it takes to reach the precision, it's clear that the total electrical consumption is much lower at a circular collider compared to a linear collider. And then the more time means also the more money you need to input because, there is a lot of budget needed to run those colliders of the order 500 or 600 million per year, right? So if it takes 50 years, then you multiply 500 million by 50 years, right? And things easily escalate very easily, right? Very quickly. So again, here. And then the last thing is also that, the more time it runs, the more carbon it will emit, right? So again, here, right, FCC is a clear winner. Clearly the linear collider will be better, for very limited precision. But as soon as you want a precision which is good enough, then it's much better to actually use a circular collider. And of course, the greener, the more ecological collider will be no collider at all, right? So you always need to normalize with the physics output that you want to achieve with these machines, right? So of course, here, I'm mostly focused on, let's say, the total cost, right? Maybe it's not the final metric that you want to use to compare the collider. An interesting quantity which is also used, by the financial people is actually the spread of, let's say, the cost over the year, right? Because you don't want to spend all your money at the beginning, then you will go into big debt, etc. Nonetheless, I think it's important to still compare things with the total cost, which is an interesting metric. Okay, so let me now jump about X physics at FCC-hh. Clearly we have seen that FCC-ee can achieve really fantastic precision measurement. So what will be the added value of FCC-hh, right? Well, certainly one important things to keep in mind is that FCC-hh will be a hadron collider, so the rate will be much higher. So it's true that you will have a huge background, but still, the number of Higgs that you will accumulate is of the order of 10 to the 10 X's that will be produced at FCC-hh. And here you can see, for instance, the ratio of the number of X's in the different production mode compared to the one that you could expect at ILUMI LHC, right? So having so many X's, allows you now to do analysis slightly differently. For instance, you can look at the distribution of those X's as a function of the PT, right? The PT of the X's. And you can see that you have so many X's that even at a PT, larger than 1 TeV, you still have many of those X's, right? That is very useful because there, the signal will be there, will still be there, but the background will drop very rapidly, right? So you can go into this extreme region of phase space, basically where the signal still exists, but there is no background at all, right? And also, one nice aspect is that, the different hierarchy of the production mode actually is changing as a function of the PT. So for low PT, the dominant production mode is gluon fusion, but if you go to higher PT, then TTH or VBF actually start being dominating over gluon fusion. So this allows you, to look at to gain sensitivity in different couplings. The other good aspect of having so many X's is that you are becoming sensitive to very rare decay mode. I mean, we have already been discussing yesterday, the interplay between high luminosity LHC and FCC-ee, right? That high luminosity LHC was very useful to enhance the sensitivity in the coupling of the X to photon or to muons, right? Or also clearly to exotics and rare BSM decay modes, right? And this will be even more true clearly with FCC-hh, where again you will have 10 billion of those X's, right? And finally, the last point, where FCC-hh also shine, is clearly in the determination of the X self-couplings, because the rate is small, so you need again a lot of energy and a lot of luminosity. And here, the ultimate precision will be a measurement of the order of few percent in the determination of the X cubic self-coupling. You could also get sensitivity to the quartic X coupling if you're interested, right? So finally, yes, let's complete the table that I showed you yesterday, where we stop at FCC-ee, and here you can see really the benefit of adding FCC-hh for the measurement of the X couplings. So, for the standard coupling to the Z, to the W, to the B, or even to the gluon, FCC-hh doesn't add much. Where it really shines is when you are looking at the rare coupling, so the rare decay modes, right? So gamma gamma, Z gamma, or mu mu, right? Also, it helps a lot. I mean, for the coupling to the top, again, because at FCC-ee you don't have enough energy to produce TTH. So you are limited in energy. You gain some sensitivity on the top Yukawa coupling simply by looking at the threshold production for the pairs of top quarks, but you don't have a direct access to TTH, where clearly FCC-hh will have far enough energy to really produce TTH. And actually, the way you measure the top Yukawa is not directly by looking at the rate of TTH, but is by measuring the ratio of TTH over TTZ in such a way that some systematics drops out from the ratio. And then again, you use FCC-ee measurement to know the electric coupling of the Z. So you know the denominator, and then by measuring the ratio of FCC-hh, then you gain a good sensitivity directly to the top Yukawa coupling, right? Below 1%. And it's important, to go below 1% because that's a coupling, right, that enter easily in the determination of the X self-couplings, right? Because X self-coupling, you look at double X production via this box, and this box involves the box of the triangle involves the coupling of the X to the top. So, if you don't know the top coupling below 1%, then you are not able to really learn about the X self-couplings. Right? Good. So talking about the X self-coupling, so the way plot is not so nice. The way you search again for the X self-coupling, the way you want to measure the X self-coupling at FCC-hh is this double X production by gluon fusion, exactly like at LHC, at high luminosity LHC, right? And here you see the behavior of this cross section, right? I mean, mostly this one, the dominant one, the gluon fusion, and you see the evolution when you crank up basically the center of mass energy, right? So going from high luminosity LHC at 14 TeV up to 100 TeV, you gain a factor, I think a factor 50 or 30 or 40, right, in the total rate. And here, this plot actually shows the behavior of the cross-section as a function of the Higgs self-couplings. Good. So the analysis that have been done for FCC-hh is actually mostly like at high luminosity LHC, focusing on BB gamma gamma, because this is where you have the highest rate, and there you use some single Higgs background. I mean, gluon fusion, VBF, TTH, and VH, and you also include some non-resonant QCD background like double photon production plus jet, etc. And the way you want to do your analysis, I mean, you first introduce a categorization in this variable, which is basically the invariant mass of the two Higgs systems, right? And then you perform a neural network discrimination to really suppress the backgrounds, right? And the result of this analysis is the following, right? So then here there is a different curve actually that corresponds to the different energy run of FCC-hh. I will come back to that, I mean, in a moment. The nominal for the CDR, in 2019, the value of the energy in the center of mass was 100 TeV. But now for the FSR, for the feasibility study, I mean, it was considered actually to run FCC-hh as a slightly lower energy, depending a little bit on the magnet again. But here it was 85 TeV, and you see basically that the impact on the determination of the Higgs self-coupling is marginal. I mean, whether you run at 85 or you run at 100 or even at 120 TeV, the sensitivity on the Higgs self-coupling vary between 3% and 5%, basically. What is maybe more interesting to control of is actually the resolution of the invariant mass of the two bottom quark, right? If you can achieve a resolution at the level here of 3 GeV, you see that basically you can gain a sensitivity in the measurement of the Higgs self-coupling very close to 1%, right? So that's an important thing maybe to optimize the gain, this resolution in the invariant mass of the two B quarks, right? So that's the main analysis. There have been other analyses that have been added, I mean, BB tau channel, and also the BB dilepton channel with missing transverse energy. So they are not fully competitive with BB gamma analysis, but they provide complementarity information and maybe sensitivity also to the other couplings. So that was a brief overview of Higgs physics, clearly at FCC-ee and FCC-hh, right? And now I will jump to the other important topics, where clearly FCC-ee is a key player, which is basically all electric physics, right? I mean, because we have already seen that you will be producing close to 10 to the 13 Z bosons, right? So this will allow you, to do a very precise line shape measurement at the Z pole, but you could also extend, I mean, electric physics up to the WW threshold production at 160 GeV. And this will translate with a 2 or 3 order of magnitude improvement compared with the current knowledge, and I will show you a table in a moment. So this is what you can expect, from the statistical point of view, but there is still a lot of challenges really to keep all the systematic uncertainties under control, right? First of all, you need a good beam calibration, at the level of 100 of kilo electron volt, right? You need to design the good detector, I mean, with high acceptance, efficiencies, and hermeticity. There is also important really to measure very accurately the luminosity, right? And then there is a calibration in situ using available data and monitoring. And then there is also the need actually of theoretical calculation, right? I mean, here, for instance, you see a table that shows the uncertainty in the various important observables, right? The mass of the Z, the width of the Z, sine squared theta effective, whatever. And you can compare the statistical, uncertainty with, didn't report it in this table, but with the theoretical uncertainties also. But one key uncertainty is really coming from the measurement of the center of mass energy, right? Which in most of the cases is actually much higher than the statistical uncertainty, right? Maybe by a factor 50 or so, right? So yeah, so there is still a lot of work to be done to really exploit all the data. Now there is two important ingredients, very two characteristic of circular collider that are very useful for electric physics, right? The first one is this beam energy calibration using resonant depolarization of the pilot benches, right? So it's not the benches that you use for physics. There is pilot benches that you will inject every 15 minutes or so in the collider. And here, they are very useful actually to measure highly precisely the energy of the beams, right? So, I mean, yeah, I won't explain for you in detail this resonant depolarization. It's something that is also used, for instance, for the measurement of G-2 of the muons, right? But what is really remarkable, I mean, this was used already at LEP, for the Z-pole, but what is really remarkable is that at FCC-ee, thanks to the size of the tunnel, actually, you can really use this depolarization measurement up to the WW threshold, right? So that's one thing for which, I mean, really the big tunnel is really a key ingredient, right? That's something that you wouldn't be allowed, for instance, at Lab 3 if you were to do, let's say, FCC in the LHE tunnel, right? In that case, this resonant depolarization will be limited to the Z-pole, and you couldn't achieve it for the WW threshold. So the prospect is just the following, right? That you will achieve a sensitivity below 50 keV at the Z-pole and up to 100 of kilo electron volt even at the WW threshold, right? So that's really impressive sensitivity. The other important ingredient is actually the luminosity measurement. So this will be done actually mostly using low-angle Babbage scattering. And this is where you expect a relative precision of 10 to minus 4 in the luminosity determination. But there are new ideas that have been proposed. I mean, using, for instance, diphoton or dimuon productions. And there is some hopes maybe to reach 10 to minus 5 or even 10 to minus 6 precision. Right? So this is still studies that are going on, but there is good new fresh ideas to improve this sensitivity. Okay, another important ingredient in all this electric measurement is actually the flavor tagging, right? I mean, there have been a nice development and improvement in this flavor tagging algorithm using in particular neural network or even AI, right? And here you can see, for instance, that it will be possible to achieve high purity, higher than 99% for the strange quark with an efficiency which is still more than 10%. And this certainly enables new measurement. For instance, using this strange tagging, you can do some SS bar charge asymmetry measurements, right? That will be useful in the global electric field. So now putting all this measurement together, I mean, I don't have time really to discuss all this observable that will be used. But here is a result, right? I mean, here you can see really a comparison of the precision achieved at FCC compared to the current knowledge, right? The current uncertainty here is reported here. You can see the statistical uncertainty and the systematic uncertainty, right? So for instance, for the mass of the Z, you see an improvement by a factor 20. For the width of the Z, it's still an improvement by a factor 200. And, I think the highest improvement is actually in the measurement of RB, by a factor 2000. You will reach 10 to minus 6 sensitivity in the measurement of RB, right? Which is quite remarkable. Even, I mean, a quantity that has received a lot of attention recently at LHE is the mass of the W, which is limited to 10 MeV at LHE. Here you will go, really below 1 MeV, right? 0.1 MeV or 0.2 MeV, right? So factor 20 improvement. So I think this table is remarkable. And then the question is, what can you do with those measurements? And I will show you some example of using this measurement, those electric precision measurement, to actually explore physics beyond the standard model. Another interesting quantity, to measure with great accuracy is actually the value of alpha QED at the mass of the Z, right? So currently, the precision is of the order of 10 to minus 4, and this is actually a limiting factor to many BSM searches, right? And here, again, there are different ways to improve this knowledge. I mean, you can do some off-pole measurement, slightly off, running the machine slightly off the Z pole, and there you will use the interference between the photon and the Z channels, that is sensitive to alpha QED. And here you can hope to get a precision of the order of 310 to minus 5, right? The only drawback of going off pole is that, of course, you are losing an event. I mean, because the cross section is certainly maximal clearly on the pole. So as soon as you are going away from the pole, you are losing event, right? And losing event means losing sensitivity. So that's why there were earlier this year there were I think a new interesting proposal to actually achieve or getting sensitivity to alpha QED by running exactly on the pole, by looking at the distribution with the scattering angle, right? By comparing, for instance, the production of electron and positron with the one of muon, because it's only for the electron that you have a T and S channel, right? For the muon, you only have the S channel, right? And in this case, you have access to alpha QED at the level of 6 10 to minus 6, right? So I mean, this is still a phenomenological analysis. It hasn't been confirmed really with detector simulation, etc. But I mean, this is still very promising, and this should be explored a little bit further, right? So yeah, what you can do now for BSM using all this measurement. I mean, clearly, you already know from lab, that you can use electric precision measurement to constrain, for instance, various models, of new physics that couple directly to the Z, right? But the remarkable thing at FCC-ee is that actually the precision, will gain sensitivity to models that are coupled at the loop level to the Z boson. So the exercise that were done, for instance, is to consider all possible one-particle extension of the standard model that have a tree-level interaction with the standard model degrees of freedom. Right? So there are about 50 of them. I mean, this has been classified a long time ago. These are all the one-particle extension that have a tree-level interaction with the standard model. Of course, not all of them have a direct influence at tree level to electric precision data. Right? Only a few of them have a coupling to the Z. Right? So those were already probed at lab. But what about the other one, right? The one that don't have a direct coupling to the Z. Right? So the thing is that they still couple at tree level, to standard model particles. So you integrate out those particles. This means that they will generate dimension 6 operator with some of the quarks, some of the leptons, right? Not necessarily operator that involves the Z. So you have those operator of dimension 6 generated at the mass of the heavy particle, and then you use a renormalization group evolution to see what is the structure of the interaction at the electric scale, right? And there, by the running, there are various mixing among the operators. And this mixing actually will draw some interaction with the Z boson, the one that can be tested directly by electric precision measurement. So this way, basically, you gain a one-loop sensitivity, to the particle that don't have a direct coupling to the Z boson. So this is exactly the exercise that was done, to see, assuming that the coupling is of order 1, to see up to which mass scale, those electric precision measurement will be sensitive to those particles, that don't couple to the Z directly. And the nice answer is that basically all of them, all these 50 particles, that couple to the standard model, actually can be probed by electric precision measurement. Some of them, at the level of 10 TeV, right? So these are, for instance, the particle that have a tree-level interaction with the Z. So here, the sensitivity will be of the order of 70 or 80 TeV. But even the particle, that have only a loop-level interaction, a loop-level induced interaction with the Z, clearly, you gain sensitivity up to 10 TeV or so, right? So this means that really there is no way to escape, if you have those new particles, there is no way to escape from electric precision measurement. And then there were various things, that were done to really get some robust determination of those sensitivity. I mean, including, for instance, the role of the theoretical uncertainty, or analyzing also the complementarity between the electric precision data on top of, let's say, the X run or the TT bar threshold. So, for instance, for some of those, here you can see that the sensitivity from electric precision data is limited, but when you add, for instance, when you add the other run, you gain a sensitivity again at the order of 10 TeV. Okay. Yeah, so basically the conclusion is that the TerraZ program gives a comprehensive coverage of new physics that couple directly to the standard model, and there is basically no way to really escape, right? So it's really a qualitative jump compared to LEP. LEP was sensitive only to new particles that couple directly to the Z. But FCC-ee will introduce a sensitivity also to new physics that have a loop-induced interaction with the Z boson. That was important. Okay. Another example of what you can probe, using this electric precision data is this study that were performed by people in Berkeley last year. They looked at basically the decay rate of the Z into 2 leptons, normalized to the standard model, and they say that this is actually very sensitive to the supersymmetric breaking scale. So, for instance, Xeno or Winos or things like that, right? And this means that, if you can measure the width with great precision, you can gain basically a sensitivity on supersymmetric breaking scale above 1 TeV. And this is exactly what those plots shows. It compares the sensitivity from electric precision measurement compared to the Dirac searches at the LHC or at LEP, right? And you see that basically, yes, you can reach about 1 TeV in this lepton, I think. Yes, this lepton, this doublet lepton on the right-handed lepton plus B also. So this really shows the power of electric precision measurement, compared to the current knowledge of Dirac searches for new physics. Good. So time is running short, so I will say a few words about QCD. What can you learn about QCD at FCC-ee? So, I mean, clearly, E plus E minus, I mean, collider is not maybe the direct place where you hope to learn about QCD, but actually there is a lot of things that are still dominated by QCD at E plus E minus collider. And here, I mean, the advantages of FCC-ee is really that you have a clean environment and a very high luminosity, right, over a broad range of energies, right? So you can really exploit this to learn a lot of things about QCD, in particular about the value of the strong coupling constant, right? At the moment, the knowledge of alpha QCD at the mass of the Z is of the order of 0.8%, the relative precision. And this is what you can hope to achieve at FCC-ee, for instance, by looking at the decays of the Z. So you measure the decay width of the Z, that include N-cube contribution, which is coming from QCD. You can also look at the ratio of the hadronic versus leptonic brushing ratio, right? And you exploit all this data basically to achieve a precision of the order of 0.1%, right? So almost 1 order of magnitude improvement compared to LHC, right? You could also exploit actually the WW threshold, right? I mean, the W's, the 10 to the 8 W's that you will produce there. And here, again, you want to look, for instance, at the width of the W, and you can reach or hope to reach a sensitivity of the order of 0.2%, right? And that's clearly an important improvement, because alpha QCD is really a key parametric uncertainty in all the prediction for the rate, right? At FCC, but also at FCC-hh later on, right? So it's really important to pin down the value of alpha QCD. There are various ideas, exploiting really, as I said yesterday, exploiting the run below the mass of the Z. I mean, to really learn about the hadronization models, or maybe to learn about the fragmentation functions, etc. So there are studies that are going on along these lines, and yeah, maybe. I mean, I'm not an expert on these things, but clearly there is things to do and to learn, if you are still interested in QCD. Top quark, so as I say, I won't discuss top quark, but I will discuss a few things about flavor physics, because there is a huge potential to learn about flavor at DESY, right? I mean, the reason is very simple, is that you're producing, again, this 10 to the 13 Z. The Z decays, in two pairs of Bs, in pairs of tau leptons, or in charm quark, right? So in such a way that you get a very large data sample, right? So this is, for instance, the yield of the production of AVB mesons, I mean, it's close to 10 to the 12, close to 10 to the 12 B mesons. Whatever, even tau leptons, is 10 to the 11 tau leptons, right? So this means that the data sample will be twice as large as the one that you will achieve at Bell 2. It won't be as large as the one that you can achieve at LHCb, right? Because hadron machines are always a higher rate, but there is still an advantage of using FCC-ee, because you simply, you have no trigger loss, you have higher acceptance, and you have a clear initial state flavor tagging, right? And the other big advantages of doing flavor at FCC compared to the other flavor factory like Bell 2 is that those AV mesons are actually produced with a high boost. At Bell 2, for instance, the B mesons are produced close to threshold, right? But here they come with a boost of a factor 6 or so, right? Simply from the decay of the Z, right? So this makes possible, I mean, really a topological reconstruction of the decays of these AV mesons, for instance, with missing energy, something that you cannot really do easily at Bell 2, right? So there is really a great advantages of doing physics, flavor physics at FCC, right? So just to give you a flavor of what can be done in flavor physics, I mean, there is this determination of the CKM elements, the measurement of the CP violating angles, gamma, beta, whatever, at sub-degree precision. There is also the determination of VCB that you will achieve by looking at the decays of the W that are produced, at 160 GeV or so. Right? So here again, the clean environment really allows you to disentangle the signal from the background, also exploiting this flavor tagging. Right? So the prospect is that at the moment there is an uncertainty of the order of 3% for the measurement of VCB, and here you hope to get to the 0.2% basically at FCC-ee, depending a little bit on the tracking performance, right? But still a huge improvement. Another sector where the improvements are really dramatic is in tau physics, again, because of the large statistic, more than 10 to the 11 pairs of tau, right? So you will be able to exploit all these taus, to perform, for instance, test of lepton flavor universalities, right? So, for instance, you will be measuring G Fermi from the tau decays at the level of 0.5 part per million, right? And then you will also put some interesting bound on lepton flavor violation, for instance, the tau decays into muon on the photon, which is at the order of 10 to minus 8 at Bell 2, at Bell. Actually, you will go by 10 to minus 9, right, at FCC-ee. The tau decays into 3 muons. The bound is of the order of 10 to minus 8. You go to 10 to minus 10 at Bell 2, but you will reach 10 to minus 11 at FCC-ee. Improvement also on the tau lifetime uncertainty or the tau mass uncertainty, right? So that's great measurement that will be exploited to learn about flavor. There is also some nice development in charm physics. I mean, charm physics is a sector which is highly interesting because, this flavor changing neutral current in the standard model are mediated by a down-type quark loop. And, peculiarity of down-type quark is that the mass degeneracy is very small compared to the mass of the W that really controls these things. This is not the case in the up quark sector because of the top, has such a mass difference compared to the other quark. But in the down sector, the mass degeneracy is much smaller. This means that all the loops are highly suppressed, right, in the standard model. So this means that it's a perfect place to look for new physics, clearly. So FCC-ee, combine the advantages of LHCb, so the Hadron machine, because you have large rate, but also the advantages of E plus E minus machine, because you have a clean environment like in Bell 2 or Bell 3. And the other good thing is that, again, you can explore that those mesons are produced from the Z decay that give you some polarization, right? So you can explore this polarization, for instance, to measure the angular observable in the decays of the charm into up and leptons, right? Something that you cannot do in PP interaction because there is no polarization of the heavy meson in this case. So there were a recent paper earlier this week, for instance, that really shows the possibilities of using FCC-ee to do some charm physics. They look at the decays of the D meson into pairs of pions and two neutrinos, and here you can see really this signal appearing very, very clearly. And this allows you to put some interesting bound for this branching ratio decay, right, at the level of 10 to minus 7. Another thing that have been looked at is the decays of these lambda mesons, right, into pairs of muons. Right? And here again, things have been reconstructed very easily thanks to the performance of FCC. Right? So clearly, yeah, FCC will be one of the best flavor factory ever. Right? So really, is going far beyond simply X factory. Right? Okay, the direct discovery potential, beyond LHC. I've already insisted at the beginning that we wanted a machine that will be exploring the energy frontier, but also exploring the intensity frontier with maybe new physics, which is light and weakly coupled, right? And again, thanks to the large number of Z, the large statistics, then you are getting sensitive to this very weakly coupled new physics. So this is clear, for instance, when you have light particle, like axion-like particle, and those axion-like particles, can be produced easily at E plus E minus collider in association with a photon or in association with the Higgs bosons, right? Like these diagrams. And here, those plots actually show the sensitivity of FCC-ee, compared to the other existing bound from astrophysics or from beam dump experiment, right? So the good news is that basically, you're extending the coverage of these ALPS models, axion-like particle model, in above basically the MEV regime, right? I mean, for long-lived particles, so for very light particle, I mean, the best bonds are coming from astrophysics, but really collider give you actually the best bond for short-lived axion-like particle in the MEV regime. There is also this mixing of axion-like particle with the standard model meson, that now you can observe, for instance, for the decay of the meson, like in Koto and NA62, K long decay into pi 0 gamma gamma via the axion or axion-like particle. And this is again, the parameter space that you will be probing as a function of the mass of the axion and as a function of the decay constant of the axion. And then there is all these long-lived particle searches, in twin X model, for instance, with some globule that mix with X and decay back into B quark, right? So all these things have been analyzed and scrutinized a little bit. So this is, for instance, a plot that shows again, the ALP sensitivity, and here you can see FCC-ee at the Z pole, or FCC-hh that will complement those searches at very high energy in this case. Right? And again, you can see the improvement compared to the existing bounds. Right? I've already shown you this plot, that shows the sensitivity to heavy neutral leptons, which is, I think, quite remarkable, that you really reach, or you fully cover the parameter space, which is compatible with the CISO explanation of the mass of the active neutrinos, right? So everything which is above this red band is actually compatible with the CISO, right? And again, here you see the sensitivity of FCC-ee compared compared to the existing bond at LHC, or compared to the bond that you expect at beam dump, right? Like SHIP, for instance. Of course, I mean, this is still limited by kinematics. I mean, clearly you cannot go, you cannot search for AV neutral lepton up to 10 to the 16 GeV. I mean, you put a bound basically up to 50 or 80 GeV. And then, I mean, you will have to rely on other machines to really explore the heavier masses. But what was interesting for me is really that FCC-ee is able to cover, this light region of parameter space. Okay, yeah. Now, I should say a few words about the exploration potential at high energy, and this will be done mostly with FCC-hh. So this is now the main parameter of FCC-hh. For the CDR that was produced in 2018, we were considering a machine running at 100 of TeV. But that might not totally be achievable, with a magnet that will be available by 2060. So we were asked actually to consider a slightly lower energy, up to 85 TeV, because that can be achieved, by a 15 Tesla magnet that should be ready easily, right? So one of the questions is, what is impact, by going from 100 TeV to 85 TeV? What kind of physics prospect you are losing by reducing the energy of FCC-hh? And this will be shown in this plot, actually, in this table. So for instance, here, you show the evolution of the X production cross-section as a function of the PT, right? For PT of 100 GeV, 140 GeV, or 100 and whatever, up to 300 GeV, you see the ratio of the cross-section for machine running at 80 TeV compared to machine running at 100 TeV. So you lose maybe 30%, for PT at 100 GeV, up to 33% for PT at 300 GeV. If instead you increase the energy up to 100 TeV, then you gain basically 30% or more events. Right? But how does it translate now in the extraction on the sensitivity of the coupling, in particular the rare couplings? This is exactly what is reported here. You can see the sensitivity, for instance, of coupling of two X's that is supposed to be 0.4% when you are running at 100 TeV. If you run at 85 TeV or 84 TeV, you will still get a sensitivity of 0.42%. Right? So it's only basically when you reduce the energy, dramatically to 70 or 60 TeV that you start losing again the sensitivity. But this sensitivity is actually compensated by increase of luminosity, right? Because if you run at lower energy, then you can gain more luminosity. Right. So the conclusion is that for the extraction of the X coupling, basically all the different scenarios are more or less equivalent with each other. Right? What about double X production? It is a key measurement for double X, right? So here you can see again the evolution of the sensitivity on the X self-coupling for a machine at 100 TeV, a machine at 84 TeV, or a machine at 120 TeV. And basically the conclusion is that the variation of those sensitivity remain within the detector uncertainty, right? You don't know yet exactly what the detector, which detector will be available, and can be easily compensate this small variation between 3% and 5% in the sensitivity on the XF couplings. This is the same exercise now for the sensitivity of FCC-hh to AV particle, and maybe a Z prime, or X-zenos and WINOs. So this is again the CDR baseline, sensitivity up to 43 TeV, right, for Z prime that decays into 2 lepton, or 18 TeV for Z prime that decays into taus or pairs of top quarks, right? So for composite quark, a sensitivity up to 40 TeV. And you see how those numbers evolve if you reduce the energy up to 84 TeV, right? You go from 43 to 37. You go from 23 to 20 TeV, right? So you don't lose much. What about the WINO and the X-zenos, right? So here the bound is of the order 4.4 TeV, you will go to 4 TeV. For the XENO, you have a reach of 1.2 TeV at 100 TeV machines, and you will go to 1.1 or maybe 1 TeV if you lower the energy up to 72 TeV. So that doesn't look very dramatic, but actually that's important, right? It's important because, for instance, in models of WIMP dark matter, this minimal dark matter model, whatever, you expect actually a limit of 1.1 TeV to reproduce the abundance of dark matter that is observed from astrophysics, right? So it will be very interesting to have a machine that can reach really this upper bound which is coming from astrophysics, right? So this is maybe the only place where it will be important to still keep a high energy. That's something that cannot be compensated by higher luminosity, right? To really reach, to really fully explore this parameter space, which is compatible with astrophysics. But otherwise, I mean, the variation is marginal. Let me come back to this plot that shows again, the projection for the sensitivity to heavy particles. And here, what you can see in particular in those numbers for the search of supersymmetric partners is that basically, you have a sensitivity up to 20 TeV, or in some cases also 40 TeV for some heavy X's, right? So the interesting thing is that we are always talking about this 10 TeV center of mass collision colliders, right? So it's always said, you always want to compare 100 TeV PP collider with a 10 TeV or 14 TeV muon collider. But here, we are dealing with a PP collider, right? So even though the dominant center of mass energy in those collisions will be of the order of 10 TeV, right? You still have a tail of events up to very high energy, exactly like at the LHE. You see some event which is much higher than 1 TeV, right? You have some event up to 5, 6 TeV. Right? And here it will be the same. I mean, you're colliding particle up to 100 TeV, and you have few events, with a characteristic energy of 30 or 40 TeV. So these events, that are rare, are still useful to really probe the existence of this heavy particle up to 30 or 40 TeV. Something that you can never do if you have a machine which is limited in energy, like a muon collider at 10 or 14 TeV. So yeah, that's the advantages of having a PP collider. Yes, I've already emphasized briefly this complementarity between FCC-ee and FCC-hh. I've told you that if you want to measure the XF coupling, then you need to know the Yukawa coupling. And the way you learn about the Yukawa coupling at FCC-hh is by measuring this ratio of TTH over TTZ, right? But you still need the input of FCC-ee in measuring actually TTZ, or to measure all this electric coupling of the top quark, right? That's exactly where FCC-ee actually is useful later on to exploit the data of FCC-hh, right? And this is what is reported in this plot, is really when you include FCC-ee together with FCC-hh that you can reach this precision of 5% at FCC-hh in the determination of the XF couplings. Otherwise, the precision by FCC-hh alone will be more like of the order of 20% or so. Yes, so that was basically an overview of what has been done for the feasibility study. So now we need to prepare certainly for the few years to come, in particular the preparation of the TDR. And we come up with this list of maybe priorities of what the community should come up with, while waiting the approval from the CERN Council. I mean, I think the most important part is really this design of the 4 detectors that are supposed to be used as the 4 interaction points, right? I think that's, you should really converge on these things. Unfortunately, there have been nice development, right? There is also important work to be done on the CERN community. So maybe that shouldn't be done, by 2028, because the data won't be there in 2028 or even in 2033. But we really need to make sure that, the CERN community makes the switch basically from LHC to E plus E minus collider again, right? Because there will be really a lot of calculations that are needed on the CERN side to really exploit all this data that will be accumulated. Another important aspect of the work ahead of us is the communication and outreach activity, in particular, for people outside collider physics, because there is all this argument, we don't know where new physics is, so we don't need a new colliders, right? But actually, we do need a new collider because these colliders are the only way we can really probe the energy frontier, right? That's the only way we can answer whether something exists or not, right? So, yeah, we need to work out on the outreach aspect of FCC to make sure that the full scientific community beyond, let's say, high energy physics really approve and understand the need for such a collider. Yep. Yes, so I think it's time probably to conclude those lectures. There will be many other things to say, but okay, we need always to come up with an end. So one aspect I would like to come back to is about the size, right? I mean, here I've discussed mostly the physics of FCC-ee, cover very briefly what can be achieved at FCC-hh, but one question is whether we need this big tunnel, this 100 kilometer, 91 kilometer tunnel for FCC-ee, right? So it's pretty clear to everybody that we need this big collider, this big tunnel for FCC-hh in order to increase the energy. But do we need also this big tunnel for FCC-ee, right? And actually, the answer is yes. I mean, there is really the advantages of having this big tunnel for several reasons. I mean, first of all, I mean, the larger the tunnel, the higher the luminosity will be, right? So in sense, there is a difference of luminosity of a factor of order 5, between a 27 kilometer tunnel and 100 kilometer tunnel. And this factor 5 is actually crucial because this is, the luminosity that you need to really gain sensitivity to the X-self coupling, to the electron-Yukawa coupling, to the sterile neutrinos, right? If you were, to run, let's say, LEP3, in the 27 kilometers, you will need to run 5 times longer to actually gain sensitivity to these things, right? And of course, I mean, you don't want a physics program that runs for 50 or 60 years to really achieve what FCC-ee could do in 15 years, right? Another aspect of the large luminosity is also for flavor physics, right? I mean, I draw some outline of flavor physics at FCC-ee, but this is only possible because you have close to 10 to the 13 Z boson, that allows you to produce all these heavy mesons, right? So if you reduce the size of the tunnel, you reduce the luminosities, you reduce the number of Z that you're producing, and then basically you are losing all these new opportunities, right? And then I told you that a crucial element for electric measurement was this transverse depolarization, right? That you really want to be available up to the WW threshold. And for that, you need a large tunnel. With a small tunnel, you can use it up to 90 GeV, but if you want to exploit it up to 160 GeV, you really need the large tunnel, right? And finally, yes, with this large tunnel, I mean, you can change the RF and really increase the energy up to 365 GeV, where you will study top quark physics, right? And that again will be really important for FCC-hh later on. So, what is the conclusion? The conclusion of Outlook, I think that during the feasibility study, FCC accelerator complex has been optimized for various considerations for geology, surface constraint, environmental consideration, local infrastructure, and accelerator performance, right? I've already told you at the beginning of all these points, right? And the outcome of the feasibility study is that now, the baseline is really 4 interaction points, right? At the time of the CDR in 2019, people were still debating whether 2 2 IP will be enough, right? But now it's clear that you gain a lot of physics by going to 4 IPs, right? Another important progress has been the design of this new RF system, which give you a total flexibility in running of the energy between 90 GeV and 240 GeV, right? And that's really, really important, to be able to switch back and forth, or also to design your run plan, because the run at the Z is very challenging. You need to control a lot of things. You need to understand your detector, your beam dynamics, etc. So it will take some time. So maybe you don't want to spend the 4 years right at the beginning to do this Z physics, and then leave people interested in flavor and X physics go away and leave the field, right? So you want maybe to run 1 month at the Z, to calibrate your detector, and then go to 240 GeV, or to go to 160 GeV, to run for 1-2 years, and then be able to go back to the Z, right? And that's possible now thanks to this flexibility, right? There is all this other science opportunity that I've mentioned yesterday, again, this light source, using this FCC complex as a light source for material science, for nuclear physics. Yeah, that's good. And another thing that also came out of this feasibility study is really the importance of FCC-ee to maximize the FCC-hh physics potential, right? It's clear that people are excited about FCC-hh because it's probing the energy frontier, but it's like doing LHC without having lab before, right? There is a few things that you need a low energy machine before to really understand things very clearly afterwards, right? And the last aspect of this feasibility study is the refined FCC-hh plan, to understand what are you gaining, what are you losing by running FCC-hh at lower energy with different magnets. Nobody knows exactly what magnet will be available in 2060. There is a lot of interesting development along this line. Maybe you will have HTS magnet, but this is not guaranteed. So you want to know whether or not it's still worth building FCC with this 14 Tesla magnet or not. So the conclusion is that FCC-ee has a rich and broad physics potential. It's really a quantum leap in testing the standard model broadly. So this is a guaranteed deliverable aspect, But at the same time, you can also search directly and indirectly for new physics, right? And it's also a perfect springboard for energy frontier known as FCC-hh. So I think the conclusion is that FCC project really perfectly fits the need of high energy physics after the LHC, right? This has been recognized clearly in the European Strategy Open Symposium in Venice at the end of June, right? And I would like to conclude by showing you some picture of the interaction point, right? So this is one of the interaction points. I think is the only one in Switzerland here, right? So this is how it looks like nowadays, and this is how it will look like in 20 years from now, right? So minimal impact clearly on the environment, right? And this is the other interaction point. Here closer to Annecy, right? This is an interaction point with some swimming pool heated by the heat of FCC, and with a very nice visitor center facing the Alps, right? And I want to emphasize that this is not an AI-generated picture, right? This is really an architect that is really thinking and working with the FCC team to really design what it could be in the future. Okay, so I think I will finish here, and there is a long list of papers that you may want to read to learn a little bit more about all this physics. Thanks.
So thank you very much, Christophe. Thanks for filling us in on a project that is impossible to summarize in 3 hours, but at least giving us a sketch of all the aspects that it involves. The floor is open for discussions. Yes, please.
Thanks again for the nice talk. So something I hadn't appreciated before was that the 90.7 kilometer ring was the benchmark for the 85 TeV with the 16 Tesla magnets. So you had put somewhere in your slides that it was 97 kilometers would be able to get to the 100 TeV with the 16 Teslas.
Yes.
So has that been considered for the FCC-ee? Because I would imagine that while it is more expensive to excavate a longer tunnel and instrument it, the synchrotron radiation goes down with 1/r². So would it actually compensate to be able to do the bigger ring in general? Because I feel like the bigger ring, the better is kind of a first order maximization that we can do.
For physics, yes, but I mean, there are other considerations, like what I was mentioning in the first lecture, right? I mean, at the end of the day, the optimal scenario is not 100 kilometers, whatever, because it doesn't really fit in the area. Maybe it will be built, I don't know, in China or whatever, but for CERN, it's not really possible.
Okay, so we really need to root for the 20 Tesla magnets if we want to see the 100 TeV proton-proton collider.
120, yes.
Okay, great, thanks.
120, you need HDS, yeah. Otherwise, I mean, also, yeah, synchrotron radiation would be far too large, and you cannot afford it.
Okay, if you can find one of your plots with the Higgs self-coupling diagram, I think you may have actually answered this yesterday, but okay, the process of having a gluon fusion and producing an off-cell Higgs that radiates another Higgs for the self-coupling measurement. So this we can do at FCC-ee also, if we ramp up the energy to 250 GeV, right?
Yes.
But is it just something that would happen like once in 10 years, we will get one event, and that's why it's completely kind of like impossible to do this, because we could, you discussed yesterday at length the possibility of changing the ZH mode to somewhere around not 240 GeV, but something else. If we would ramp it to 250 GeV, we would, in theory, in principle, we would produce some events that also would be probing the Higgs self-coupling, but this is just like statistically absolutely impossible.
Statistically limited, yeah.
Yeah. But also, I guess for the FCC-hh, it will be limited with the exact same backgrounds. I guess it's ZH hadronic decays, but then you just get the numbers that you get enough of these events that you can get some something out of it.
Yeah.
Okay, thanks.
So I give the word shortly to myself.
Okay.
You mentioned in this draft do list towards the TDR, you mentioned the theory line. It was number 5 or 6. Now it's clear that theorists worldwide, the worldwide community, should substantiate its input as far as possible.
Yes.
But from the point of view of your preparation, can you identify areas where this would be much more needed than other areas? So in other words, I take it for granted that the community has to refocus irrespective of what happens. After an area of hadron collider, we move to an E+ E- collider physics, and that's the challenge. But from your study, can you say which fields would deserve from the theory side most attention and are in some sense not as ideally stuffed as you would like?
I mean, it's clearly for all the electric processes, right? I mean, to exploit all this data at the Z, you need to go to free loops, something like that, and this is really not available. In principle, I mean, that's theoretical technique that can be inherited from LHC, but you really need to go one loop, I mean, more, and that's not easy, and takes time really to build a community that can do that.
There is the challenge is not only an industrial challenge of doing what is in the textbook, but that you really have to have new ideas, both on the computing side and conceptually about how to organize these calculations.
Absolutely.
So it should not be perceived as continuing to do what is done in precision theory, but as always, an order more is a transformative change.
Yes.
Well, I thought it's helpful to clarify that. Questions, more questions. One shouldn't start with end these 3 nice lectures with a theory question, given that it's an experimental project. But of course we can.
But you also need to come up, I mean, to continue along your question, you also to come up with new observables, like for instance, what I mentioned for alpha QED measurement, right? And go on pole, but using this angular distribution is something that was not thought before. But you need theories to think about those observables that could be exploited later on.
Okay, so there is another question.
Yeah, Christophe, thanks a lot for the lectures. You convinced me. I think FCC is a great idea. So for the magnets, if we go to the experiment a little bit more, I was wondering, I understand that we potentially in the baseline scenario want to opt for something we kind of can do. And of course, there needs to be R&D getting into these magnets as well. But let's say new physics is at 93 TeV. It would, of course, be very bad if we built, an 80 TeV machine and then we miss by 13 TeV.
Yes.
So do you have an idea, like the R&D effort being put in the stronger magnets, if this will receive as much funding as the baseline scenario?
For sure. I mean, there is a huge magnet R&D that is gone to produce HTS magnet. I mean, I don't think they will run short of money for that, right? Because it's so important for all the things beyond really collider that people are excited to do that. Now you need to check what can be used for collider physics later on. But I don't know. I'm not an expert on magnets. There are people at CERN that are. It's also nice. I mean, for them to give motivation to really, improve their magnet for the use of particle physics. So.
Yeah. So another question, please. So, Mark.
Hi, so I actually have a question about the Higgs width. So one thing that you stressed a lot is that already with the FCC-ee, we can very well constrain the Higgs width because we don't need the decay side to obtain the value. It seems to me that would be also very interesting for reinterpreting a lot of LHC data, because I feel like whenever we're looking, for example, in the context of SMAFT interpretations at decay side operators, we are extremely constrained by the Higgs width. Yes. So even if we have some sensitivity when we inject the EFT only at that specific channel, we're completely constrained by the width. So being able to reinterpret that with the updated values of the Higgs width should give you some constraints, at least on where perturbativity breaks. I mean, you cannot straight away say there's new physics, but what I wonder is there's also the concern of the different decay channels affecting each other. So in this kind of catastrophic situation in which even though the Higgs width is very standard model-like, it's just because every single decay channel happens to somehow cancel out and then the Higgs width stays standard model. So do we know how much this could improve the reinterpreting of the LHC results? Or
well, okay, as I said yesterday, at LHC there is no real measurement of the width, right? There is interpretation of the width after putting some assumption, right? I mean, the typical assumption is to say that the kappa v, the interaction of the x to the w and the z, are not larger than the standard model. So this gives you an upper bound, and this upper bound, is enough to leave the flat direction between, rescaling all the coupling and at the same time introducing a new contribution to the width, right? So again, at LHC, you need to put assumption if you want to put a bound on the width. This is in principle not the case, or at least the assumptions are slightly milder at a E plus E minus collider, because the energy, the colliding energy, right? So then you can exploit this recall mass. You don't need to look at the decay of the X, and you take the ratio, of the inclusive production with the exclusive production with the X decays, and then you have access to the X width. But now, if you want, to exploit, let's say, the constraint on the width, you need to make sure that you fit under the assumption, right? I mean, for instance, LHC assumptions. So if you fit within those assumptions, then it's fine to use LHC. And then in that case, FCC-ee measurement won't add much, because at the end of the day, the constraint on the width is not dramatically improved compared to the indirect determination of the width at high luminosity LHC. But the key thing is really under the assumption, right? The assumption that you are making to extract this constraint.
Sorry, just to add one thing. What I more mean is that even though you can get a pretty good constraint under a lot of assumptions,
right.
A lot of the time when you look at decay side, so you really want to look at the decay side, we let the width go as crazy as it wants in this mapped interpretations because we want to avoid those assumptions. So I feel like just making use of the high luminosity that we have already at FCC at LEC, just with like this single measurement of the Higgs width with less assumptions that could already like change completely the.
So you're talking mostly about the untagged decay rate in that case. Right? So you cannot reconstruct the decay mode of the Higgs.
I more mean when we always need, as you said, the Higgs width. Right. To be able to measure any Higgs decay, right? We input the value of the Higgs width, but if you try to look at any operator that is changing the partial decay, you need to also include this operator in the Higgs width, and that there is where we have very large values. It's more what I meant, but maybe you can discuss.
We can discuss.
Thank you. Sorry.
Have two more questions, I think. First,
yes, it was just a comment for the question before yours on the energy with the 14 Tesla or more. I also say that 84 is now the baseline for the FSR. We are working in the same magnet strength to further optimize the cell. I would say that 88 is on its way, and we hope 90.
Then we have also Matthew.
Yeah, thanks, Christophe. So it's very clear the FCC is the perfect machine to match the science of today, this unknown what's next after the Higgs, etc., and the lack of BSM so far. Is there a discovery that's conceivable in the next 10, 20 years that could severely weaken or derail the physics case for FCC, either high lumi or neutrinoless double beta decay, EDM, sterile news? I mean,
it could be. I mean, in a sense, I don't know, if you discover weakly interacting particle as 500 GeV or 600 GeV, right? So then, you won't have enough energy at FCC-ee to produce this particle, and then it's weakly interacting, so, it's not best studied at FCC-hh. Now the question is, what are the constraints on such weakly interacting particle at 500 or 600 GeV?
Okay.
Yeah. I mean, then you could also probe that indirectly, not directly in that case, but I mean, as I show, using electric precision data, in principle, you could really learn about those particles, but it will be only indirect in that case. Right? So
if he asks, let me test that statement you made a bit further, because assume whether it's G-2, assuming that you understand something, or neutrinos double beta decay, you would have first indirect evidence that there is something not explained by the standard model. You wouldn't have produced the missing piece. So again, you would be tempted to look, where is the infrastructure to get from a tension or a deviation from the standard model to a production where you can focus on the new phenomenon. Then clearly, whether you think that then you can't say that there's an egg-laying wool milk sow that can address all hypothetical scenarios where tensions could occur that are observed on a lower energy scale. But one could turn the question around and say, you could say, is FCC-ee a machine to follow up on conceivable scenarios of where constraints appear? Say you find a problem in the flavor sector, and you had evidence that in terms of lepton flavor universality violations, these B decays you showed would have a reach that goes significantly on top of LHCb physics. So clearly, then you don't make the general legal statement that everything is in dry clothes, but you say still this is a scenario. This is a machine. This provides an infrastructure to follow up on a significant amount of the eventualities. I don't want to put words into your your mouth, but I wonder whether this is an argument that can be better defended, that I can do it as a stand-up comedian.
I mean, I don't know, there is different aspect to your question. I mean, it's true that there are probably, you know, physics scenarios where FCC wouldn't be the best machine to probe these scenarios, right? And on the other hand, I mean, you don't want, you know, to motivate the next collider by saying, well, there is this particular scenario where I need this machine, right? You want a machine which is broad enough to cover all possibilities. And that's exactly what FCC-ee is doing, right? Even this particular case, you know, for 500 or 600 weakly interacting particle, you will have evidence for this particle at FCC-ee indirectly, but you will have evidence, right? So in that sense, you have a machine where new physics doesn't escape, right? And that's the important thing, because, you know, we have no clue at the moment where new physics really is, right? So we need really a broad and versatile machine.
By the way, so I think at some stage we should thank you and realize that we will not explore all questions that we can explain, that we can expect on the project. I think it's a very good sign that the last question was raised from someone from CERN's press office, because you had on your draft do list of the TDR also the question about how to put this rich physics in words. And that's certainly not something that we settle in a question of answers session. And that is in some sense a project that is as important as the other 11 projects here. And possibly that's a good way to end, except that we should leave you the last word. And then, of course, you get a handful of applause because you did really a magnificent job. So if there's nothing really more, this was the first of quite a few academic training lectures during the FCC area.
The next 50 years, maybe.
And we thank you for having given them. Okay.
Thanks.